Far out beyond the orbit of Neptune, drifting in the frozen darkness where sunlight is little more than a faint star, there exists a world so strange it defies everything we thought we understood about our solar system. This distant object, known as Quaoar, orbits in a region called the Kuiper Belt, a vast expanse of icy bodies left over from the formation of our planetary neighborhood. But Quaoar is no ordinary relic. It holds secrets that have left astronomers both puzzled and thrilled, presenting mysteries that challenge the very foundations of planetary science. What makes this small, distant world so extraordinary? Why has it become such a compelling puzzle for those who study the cosmos? Imagine a place where the rules of physics seem to bend, where rings exist where they shouldn't, and where the very nature of what makes a planet or a moon is called into question. Quaoar is that place. Discovered just over 2 decades ago, it quickly stood out not for its size or brightness, but for the baffling phenomena associated with it. From its unexpected ring system to its peculiar composition and orbit, each aspect of Quaoar invites more questions than answers. It's as if this distant world is deliberately whispering riddles across the vastness of space, daring us to listen and unravel its enigmas. Today, we embark on a journey to explore 25 of the most captivating mysteries surrounding Quaoar. Each of these puzzles opens a window into the complexities of our solar system and reminds us that there is still so much we have yet to learn. Whether you're a long-time space enthusiast or simply curious about the universe, this exploration will take you to the edge of known science and into the thrilling realm of discovery. So settle in and let's venture together into the deep and mysterious wonders of Quaoar. Our journey into the unknown begins with perhaps the most baffling of Quaoar's many puzzles. Astronomers have spotted a ring system encircling this distant world, a feature that in itself is not entirely unique. What makes this ring so extraordinary, so deeply confounding, is its location. It exists in a place where, according to all our established rules of celestial mechanics, it simply should not be able to exist. This rule is known as the Roche limit. It's a fundamental concept in astronomy that defines a critical distance around any planet or large body. Inside this limit, the gravitational tidal forces from the main body are so powerful that they overwhelm the self-gravity holding any smaller object together. This is why rings form. Within the Roche limit, any loose material, be it dust, rock, or ice, is torn apart and prevented from ever accreting into a solid moon. Outside this limit, however, those same forces weaken significantly, allowing that very material to gradually clump together and form a natural satellite. For over a century, this principle has been a cornerstone of our understanding, explaining the beautiful rings of Saturn and the orderly orbits of moons around countless other worlds. Quaoar's ring, however, laughs in the face of this long-held rule. It sits far outside its calculated Roche limit, so far out, in fact, that the particles within that ring should have coalesced into a moon within just a few decades, perhaps even a few years. It's the equivalent of finding a perfectly sandblasted sculpture standing untouched in the middle of a hurricane. The forces at play should have destroyed it long ago. Yet there it is, a tenuous band of debris stubbornly holding its formation against all odds and expectations. This discovery has sent a shockwave through the field of planetary science, forcing a profound and humbling reconsideration of what we thought we knew. If our models of the Roche limit are correct, which they have been for every other instance we've observed, then Quaoar's ring is an absolute impossibility. That leaves only one conclusion: our models must be incomplete. There is some other force or phenomenon at work here that we have not yet accounted for, a hidden variable in the equation of orbital mechanics that is acting as an invisible shepherd, keeping these particles in a stable ring against the relentless pull of gravity. Scientists are now racing to propose theories for what this mysterious force could be. Could it be the gravitational influence of Quaoar's known moon, Weywot, creating stable points that corral the debris? Perhaps the particles themselves have unique physical properties, like a strange elasticity or a static charge that allows them to gently collide and bounce apart instead of sticking together. Or maybe, just maybe, there are other small, unseen moons orbiting within this ring, their tiny gravitational nudges providing just enough structure to maintain this cosmic halo. Each theory is compelling, yet none yet offer a complete answer. This single, faint ring around a small world in the darkness of the outer solar system has effectively thrown a wrench into the gears of planetary formation theory, proving that even our most fundamental assumptions are still open for debate. This peculiar absence of an atmosphere leads us directly to our second great puzzle, the case of Quaoar's missing gaseous shroud. Here we have a world that, by all rights, should be cloaked in a thin veil of gases. It sits in the same frigid neighborhood as Pluto, and while it is a bit smaller, its size is still significant enough that its gravity should be capable of capturing and holding onto certain volatile compounds. Pluto, as we know, boasts a complex and tenuous atmosphere that waxes and wanes with its seasons, primarily composed of nitrogen with traces of methane and carbon monoxide. So why does Quaoar, a seemingly comparable Kuiper Belt object, appear to be completely and utterly bare? The most straightforward explanation points to a process known as atmospheric escape. In the simplest terms, a world can only hold onto an atmosphere if the speed needed to escape its gravitational pull, the escape velocity, is significantly higher than the average speed of the gas molecules in that atmosphere. If those molecules are too fast and energetic, they can simply fly off into space. For a cold world like Quaoar, this shouldn't be a major issue. The bitter cold should slow molecules down, making it easier for gravity to keep them anchored. However, Quaoar's journey around the Sun is not a perfect circle. Its elliptical orbit brings it considerably closer to the Sun at some points than at others. During these closer approaches, the weak sunlight could provide just enough warmth to give lighter gas molecules like nitrogen or methane the energy boost they need to achieve escape velocity, venting any potential atmosphere into the void over millions of years. But this thermal escape theory, while plausible, might be too simple an answer. Another compelling idea involves Quaoar's very composition. What if it simply never accumulated a substantial amount of the volatile ices that vaporized to form atmospheres in the first place? The building blocks of the outer solar system were not uniformly distributed. It's entirely possible that the region where Quaoar formed was curiously depleted in the light, fluffy ices of nitrogen, carbon monoxide, and methane that are so abundant on Pluto. Instead, Quaoar's bedrock might be dominated by heavier, more refractory materials like water ice and rock, substances that remain solid at the temperatures found in the Kuiper Belt and thus cannot contribute to a gaseous envelope. It may be a fundamentally different class of object, a relic from a chemically distinct part of the primordial solar nebula. Perhaps the most intriguing possibility is that we are witnessing the effect of some unknown atmospheric suppression mechanism unique to this world. Could Quaoar's surface be acting like a cosmic cold trap? Its surface temperature is incredibly low, even for the Kuiper Belt, potentially cold enough that what little volatile ice exists is permanently frozen solid to the surface, unable to sublimate into a gas at all. It's as if the entire world is locked in a perpetual deep freeze. Another fascinating, though highly speculative, theory suggests that Quaoar's strange ring system might be playing a role. The particles in the ring could be actively sweeping up any stray gas molecules that try to form, effectively acting as a dynamic vacuum cleaner that prevents an atmosphere from ever getting started. Each of these explanations offers a tantalizing glimpse into the complex and varied processes that govern these distant worlds, reminding us that the rules of planetary science are still being written. This unusually lethargic spin presents a genuine puzzle when we compare it to its neighbors. Most other sizable objects in the Kuiper Belt, like Haumea, whiz around at a breakneck pace, completing a full rotation in just a few hours. This rapid spinning is often a relic of their formation, a conserved momentum from the countless collisions and accretion events that built them billions of years ago. Quaoar's leisurely 17.68-hour day stands in stark contrast to this norm, suggesting its rotational history was dramatically altered somewhere along the way. Something had to have applied the brakes, and astronomers are investigating several compelling possibilities for what that cosmic brake pedal might have been. One of the leading theories points to a violent and dramatic event in Quaoar's deep past, a colossal off-center impact. Imagine another large icy body, perhaps even a protoplanet, smashing into Quaoar in a glancing blow. Such a catastrophic collision wouldn't just leave a crater, it could fundamentally transfer enough angular momentum to dramatically slow the world's spin. It's a scenario we see evidence for elsewhere in our solar system. The most famous example is our own Earth, where a giant impact is the prevailing theory for the formation of our moon and is also thought to have significantly altered our planet's initial rotation rate. A similar enormous crash could easily explain Quaoar's current sluggish turn, leaving it with this lasting signature of an ancient traumatic encounter. But a smash-up isn't the only potential explanation. Another strong candidate involves Quaoar's gravitational relationship with its own moon, Weywot. This process is known as tidal locking, and we see it in action all over the solar system. Our moon is tidally locked to Earth, which is why we only ever see one side of it. The gravitational pull between two bodies creates a slight bulge, and as the smaller object orbits, it tugs on that bulge, creating friction that gradually drains rotational energy. Over billions of years, this tidal friction can slow a planet's spin until it becomes synchronized with its moon's orbit. It's entirely possible that Weywot's gentle, persistent tug has been acting as a steady brake on Quaoar, sapping its rotational momentum to create the slow spin we observe today. This would imply a long and intimate orbital dance between the two, a gravitational partnership that has fundamentally shaped Quaoar's present state. Yet a third possibility invites us to consider what might be happening deep within Quaoar itself. What if its internal structure is uniquely engineered to resist spinning faster? We often think of these distant worlds as simple balls of ice and rock, but they can have surprising internal complexities. Quaoar could possess an unusual mass distribution, perhaps a very dense, rocky core that is significantly offset from its center, creating an inherent instability that prevents a faster rotation. Alternatively, its internal composition might make it unusually dissipative. If its interior is partially differentiated with layers of slushy ice or even a subsurface ocean, the friction between these layers as the world turns could act as a built-in damper, systematically converting its rotational energy into heat and bleeding it away into the frigidness of space. This would mean Quaoar's slow spin is not a scar from a past event, but an ongoing characteristic dictated by its very own internal engine. Yet the existence of such a large moon for a relatively small parent body is itself a subject of intense debate. The most widely accepted theory for the formation of moons in our solar system points to a giant impact. In this scenario, a massive collision early in Quaoar's history would have blasted a tremendous amount of debris into orbit around it. Over time, this debris would have coalesced under its own gravity to form Weywot. This is the very same process we believe gave Earth its own large moon. For Quaoar, however, this theory runs into a significant problem of scale. For an impact to eject enough material to form a moon the size of Weywot, the colliding object would have had to be enormous, perhaps so large that the impact might have completely shattered the proto-Quaoar instead of leaving it intact with a single large satellite. The violence required seems almost too much for the system to have survived. This leads to an alternative, though even more complex, possibility: capture. Perhaps Weywot did not form alongside Quaoar, but was instead an independent object, a wandering denizen of the Kuiper Belt that ventured too close and was gravitationally snared by Quaoar's pull. While this would sidestep the issues of a formation impact, it introduces a host of new mechanical puzzles. Gravitational capture is incredibly difficult to achieve naturally. An object flying past another needs to lose a significant amount of its orbital energy to transition from a flyby into a stable orbit. This usually requires a secondary mechanism to act as a brake, such as atmospheric drag or an interaction with a third body. In the airless, sparsely populated depths of the Kuiper Belt, neither of these braking systems are readily available, making a clean capture event seem highly improbable. The intrigue deepens when we consider Weywot's composition, another layer of this multifaceted mystery. Is it a chip off the old block, made of the same mixture of rock and water ice as its parent? Or is it a captured alien world composed of entirely different materials that tell a story of origins far from Quaoar? Its dark surface, which suggests a coating of complex organic compounds known as tholins, mirrors the darkness of Quaoar itself. This could be evidence for a shared origin, as both bodies have been subjected to the same eons of radiation from space. Conversely, that dark coating could be a common feature among many Kuiper Belt objects, telling us nothing definitive about where it was truly born. Without a close-up visit from a spacecraft, its fundamental recipe remains a guess, leaving us to wonder if we are looking at a native child of Quaoar or an adopted orphan from the frozen reaches of space. This gravitational interplay might also hold the key to other Quaoar mysteries, potentially even playing a role in shepherding the particles of its impossible ring. The dance between Quaoar and Weywot is a dynamic, ongoing relationship that has sculpted the system we see today. Every peculiarity of Weywot's orbit is a clue, a fossilized record of the forces that have acted upon it over billions of years. Unlocking its secrets would provide a window into the violent and chaotic early history of the outer solar system, a time when collisions were frequent and orbits were dramatically rearranged. Weywot is more than just a moon. It is a silent witness to the past, and its puzzling presence challenges our understanding of how even the smallest of planetary systems come to be. Just when we thought Quaoar couldn't get any more perplexing, its very light reveals another layer of mystery. Astronomers tracking this distant world have documented strange and unpredictable variations in its brightness. Unlike the steady, rhythmic pulse of light we see from rotating asteroids with distinct dark and light sides, Quaoar's flickering is irregular and inconsistent. This isn't a simple case of one dark hemisphere and one bright one turning in and out of view. Something far more dynamic and enigmatic is happening on its surface, causing its reflectivity to change in ways that defy easy explanation. One compelling possibility is that Quaoar's surface is not a uniform blanket of ice and rock, but a complex patchwork of different materials, each with its own unique ability to reflect sunlight. Imagine vast plains of brilliant, clean water ice sitting alongside fields of dark, tar-like organic compounds. As Quaoar slowly rotates, these contrasting terrains would come in and out of our view, creating a shifting pattern of light and dark. The irregularity of the changes suggests this isn't a simple two-tone world, but a mosaic of many different compositions. Perhaps recent impacts have excavated bright, fresh ice from beneath a dark, irradiated crust, creating brilliant spots that gradually fade over time as they are bombarded by cosmic radiation. This surface could be a constantly evolving tapestry, with its brightness variations acting as a direct window into its active and diverse geology. An even more thrilling theory points to ongoing geological activity, specifically a process known as cryovolcanism. This isn't the fiery, lava-spewing volcanism we know on Earth, but a frigid counterpart where slushy mixtures of water ice, ammonia, or methane push up from a warm interior and erupt onto the surface. A cryovolcanic eruption would coat the surrounding landscape with a fresh, highly reflective layer of bright ice, dramatically increasing the albedo or reflectivity of that entire region. If such eruptions are happening sporadically across Quaoar, they would create temporary bright spots that appear, persist for a while, and then slowly darken, perfectly explaining the irregular brightening events we detect from Earth. This would mean Quaoar is not a dead, frozen relic, but a geologically active world with a complex and warm interior, a concept that radically changes our understanding of objects in the distant Kuiper Belt. We must also consider a more subtle and unusual phenomenon, the temporary presence of a faint seasonal atmosphere. While we believe Quaoar lacks a permanent gaseous shroud, it's possible that when its elliptical orbit brings it closest to the Sun, the slight increase in solar warmth might be enough to trigger the sublimation of the most volatile ices on its surface, like nitrogen or carbon monoxide. This could generate an extremely tenuous, transient atmosphere that hangs over the world for a short period. Such a haze, even if incredibly thin, would act like a diffuse mirror, scattering sunlight and making the entire object appear marginally brighter from our vantage point. As Quaoar moves away from the Sun and cools again, this temporary haze would collapse back onto the surface as frost, causing the brightness to fade. This cycle could create a slow, seasonal pulse of brightening superimposed on the more random, smaller variations, adding another complex rhythm to the light curve we observe. Each of these explanations paints a picture of a far more active and complex world than its frozen location would suggest. The unexplained brightness variations are not merely a curious observation, they are a vital clue. They hint at a surface that is actively being reshaped, whether by internal forces, external impacts, or seasonal cycles. This flickering light is a message, a Morse code transmitted across billions of miles, telling us that Quaoar is dynamic, evolving, and utterly fascinating. The enigmas only deepen when we turn our instruments toward the subtle whispers of heat emanating from this frozen world. Here, in the perpetual deep freeze of the Kuiper Belt, where temperatures are expected to hover just a few dozen degrees above absolute zero, Quaoar presents us with a thermal puzzle. The heat radiation we detect from its surface is subtly but unmistakably warmer than our models predict for an object of its size, composition, and distance from the Sun. It's as if this distant sphere of ice and rock is generating its own warmth, a faint but persistent fever that defies the icy grip of its surroundings, forcing us to ask what could possibly be cooking inside this seemingly inert world. One of the most exciting possibilities is that Quaoar is geologically active, possessing a source of internal heat that is slowly leaking out to warm its surface. For a long time, we believed objects this small and this far from the Sun were essentially dead, their interiors frozen solid billions of years ago, but Quaoar might be challenging that assumption. This internal warmth could be generated by the decay of radioactive elements within its rocky core. Elements like uranium, thorium, and potassium release heat as they naturally break down over immense timescales. If Quaoar's core is sufficiently large and rich in these radioactive isotopes, it could act like a built-in nuclear furnace, providing just enough energy to elevate the temperature above what would be expected from solar heating alone. But there's another, even more compelling source of heat to consider: tidal flexing. This process generates tremendous internal energy through gravitational friction, and we see it most spectacularly on moons like Jupiter's Io or Saturn's Enceladus. For Quaoar, the key could be its gravitational relationship with its moon, Weywot. If Weywot's orbit is even slightly non-circular or eccentric, the gravitational pull between the two bodies would constantly change. This varying tug would rhythmically squeeze and stretch Quaoar's interior, much like repeatedly flexing a piece of metal until it becomes hot. This friction would convert orbital energy into heat, potentially maintaining a layer of liquid water, a subsurface ocean beneath a thick icy crust. The idea that a world so far from the Sun could harbor a hidden ocean is revolutionary, suggesting that habitable environments might exist in the most unexpected corners of our solar system. We must also consider that the anomaly might not be in the heat itself, but in how that heat is being trapped and released by Quaoar's surface. The way an object emits thermal radiation is heavily influenced by its surface texture and composition. Imagine a blanket of fresh, fluffy snow on a cold winter day. It is an excellent insulator because it is full of air pockets. Similarly, if Quaoar's surface is covered in a layer of highly porous, frothy ice or a fine, dust-like regolith, it could act as a fantastic insulator. This blanket would trap internal heat, preventing it from escaping efficiently into space and causing the surface to register as warmer than anticipated to our telescopes. The surface wouldn't be generating the heat, but simply holding it in, creating a misleading thermal signature. Of course, we have to address the possibility that the anomaly isn't coming from Quaoar at all, but is instead a trick of our own perception. Measuring the temperature of a pinprick of light 4 billion miles away is an extraordinarily difficult task. The readings could be skewed by a phenomenon called surface roughness. If Quaoar's landscape is not smooth but incredibly rugged, filled with deep craters and sharp cliffs, those topographic features would create microscopic variations in temperature. Sunlight warming one side of a crater wall while the other remains in shadow could create a complex thermal patchwork that our distant instruments struggle to interpret correctly, averaging out to a value that appears anomalously warm. There's also the potential for confusion from a different direction entirely, background contamination. Our telescopes are staring across an immense gulf of space, and their line of sight to Quaoar is never perfectly clear. It's possible that the faint extra warmth we detect is not from Quaoar itself, but from a faint, unknown background galaxy or a cloud of distant dust lying somewhere along the same path, its signal inadvertently blended with Quaoar's. While astronomers work meticulously to subtract such interference, the possibility of a subtle, unaccounted-for signal remains a constant challenge in the field of observational astronomy. This thermal mystery is far more than a technical discrepancy. It is a fundamental question about the very nature of this distant world. Is Quaoar a dynamically active body, warmed from within by radioactive decay or the gravitational friction of its orbital dance? Or is it a brilliantly deceptive world, using a blanket of exotic ice to mask its true coldness? Each answer points toward a radically different understanding of what Kuiper Belt objects can be, transforming them from simple frozen fossils into complex, evolving worlds with their own unique stories of heat and light. Just when we think we're beginning to understand the basic ingredients that make up this distant world, Quaoar presents us with a chemical puzzle that seems to defy logic. Through the powerful eyes of our most advanced telescopes, astronomers have performed spectroscopy on the faint light reflecting off Quaoar's surface, breaking that light down into a spectrum that acts like a fingerprint, revealing which molecules are present. The results are a confusing and contradictory cocktail. They clearly show the signature of crystalline water ice, but also point to the presence of more volatile ices like methane and possibly even ammonia hydrate. On the surface, this might not seem unusual. After all, we find these ices on other Kuiper Belt objects like Pluto. The true mystery lies in the specific proportions and the state of these materials, combinations that simply don't fit any of our established models for how such a body should have formed and evolved over 4 billion years. Take the water ice, for example. The spectrum suggests it is predominantly in its crystalline form. This is a crucial detail. Water ice can exist in two main states: amorphous, where the molecules are in a disordered, glass-like state, and crystalline, where they are arranged in a regular, structured pattern. In the frigid environment of the Kuiper Belt, where temperatures are perpetually near absolute zero and radiation from the sun is incredibly weak, water ice should naturally exist in the amorphous state. For it to become crystalline, it requires a significant input of energy enough to heat the ice to around -150 degrees Celsius so the molecules can rearrange themselves into order. The persistent presence of crystalline ice across Quaoar's surface therefore implies that some process must have provided that energy, repeatedly warming the ice enough to transform its fundamental structure long after the world itself was formed. Then we have the methane. Detecting methane itself isn't the surprise, it's its apparent stability that baffles scientists. Methane is a highly volatile compound, a gas that sublimates into vapor even at the extremely low temperatures found at Quaoar's distance from the sun. On a small world with relatively weak gravity, this gas should have escaped into space eons ago, leaving the surface utterly depleted. Its continued presence suggests one of two extraordinary possibilities. The first is that Quaoar is somehow continuously replenishing its methane supply, perhaps from an internal reservoir that slowly leaks the gas to the surface through cryovolcanic processes or from cracks in its crust. The second, even more intriguing possibility is that the methane isn't pure but is instead trapped within other, more stable materials. It could be locked away in cage-like structures called clathrates, where water ice forms a molecular prison that holds the methane molecules captive, preventing them from escaping. Alternatively, the methane might be chemically bonded with other elements, creating new, more complex tholin compounds that are far less volatile and can persist on the surface for billions of years. This leads to the greatest contradiction of all, the apparent coexistence of these materials. Our current models of planetary formation suggest that objects in the Kuiper Belt condensed from a solar nebula that had a specific chemical gradient. Objects that formed in different locations or at different times should have ended up with distinctly different compositions. Quaoar's mixture of water ice, methane, and potential ammonia seems to borrow aspects from several different classes of Kuiper Belt objects, creating a blend that is entirely unique. It's as if this world was assembled from parts that originated in vastly different regions of the early solar system, a possibility that challenges our understanding of how this distant belt of debris was originally populated. One compelling theory to explain this chemical jumble is that Quaoar is not a primordial pristine body but a complex world that has undergone significant geological processing. Its interior may have warmed enough in the past to partially melt, creating a subsurface ocean that allowed different compounds to mix and react before refreezing. This could explain the transformed water ice and the complex organics. Alternatively, Quaoar could be the product of a colossal merger between two or more smaller bodies that each had very different chemical compositions. A gentle, slow-motion collision could have mashed a methane-rich object together with an ammonia-rich one and a water ice-dominated one, creating the hybrid world we see today without the violence that would have boiled all the volatiles away. Each layer of spectral data we gather deepens the mystery, revealing a world that is not a simple relic but a complex chemical factory whose recipe we are only just beginning to decipher. Beyond the familiar orbits of the planets, the outer solar system operates on a grand, rhythmic clockwork of gravitational harmony, a celestial dance where orbits align in precise, stable ratios known as resonances. These relationships act like cosmic ballets, where one object's orbital period is a simple fraction of another's, creating a repeating pattern that prevents chaotic collisions. Neptune, as the gravitational heavyweight of this region, is a master conductor of this dance, shepherding countless Kuiper Belt objects into these stable resonant patterns. This is why Pluto, for instance, completes 2 orbits around the Sun for every 3 orbits of Neptune. It's locked in a stable 2 to 3 resonance that protects it from being ejected. Given this orderly symphony, astronomers expected a world of Quaoar's size and proximity to also be gracefully locked into a resonant step with the giant planet. Yet, when they calculated its path, they found something profoundly puzzling. Quaoar is a maverick dancing entirely to its own tune, existing in a gravitational no-man's land with no discernible resonant relationship with Neptune at all. This absence of resonance is a genuine conundrum. The prevailing model of our solar system's history, known as the Nice model, describes a period of dramatic planetary migration billions of years ago. As the giant planets shifted their positions, their immense gravity would have swept through the primordial Kuiper Belt, either capturing objects into stable resonances or violently flinging them into the scattered disk or out of the solar system entirely. For an object as large as Quaoar to have survived this cosmic upheaval without being captured into a resonance is statistically unusual. It suggests one of two extraordinary possibilities. The first is that Quaoar is a remarkable survivor, a lucky object that somehow managed to weave its way through the shifting gravitational tides without being caught, like a stone skipping across a churning ocean without sinking. The second, more radical idea is that Quaoar did not originate in its current location at all, but formed much closer to the Sun and was later gently placed into its present orbit by the migrating planets, avoiding the violent scattering that affected so many others. The intrigue doesn't stop with Neptune. Scientists have also searched for any hint of resonant relationships between Quaoar and other large denizens of the Kuiper Belt, like the dwarf planets Haumea or Makemake. Once again, they've found nothing. Quaoar appears to be a true solitary wanderer, its orbit a unique signature that doesn't harmonize with any of its major neighbors. This profound isolation makes it a critical outlier, a data point that doesn't fit the neat categories we've created. In science, it's often the exceptions that reveal the most, and Quaoar's rebellious orbit forces us to reconsider the violence and complexity of the solar system's early days. Its path is a fossilized record of that chaotic era, and its lack of resonance implies that the process of planetary migration and orbital capture was far messier and less complete than our best models suggest. Unlocking the secret of Quaoar's orbit could therefore rewrite chapters of our own history. If it truly avoided capture, its current trajectory might preserve a pristine record of the conditions in the protoplanetary disk before the giant planets began their great migration. It could be a time capsule holding clues about the distribution of mass and the strength of gravitational interactions in the solar system's infancy. Alternatively, if it was placed in its orbit by a specific and gentle gravitational interaction during the migration, it would point to a more nuanced and complex series of events than we currently understand. Quaoar's silent, resonant-less journey is a deep and fundamental mystery, a quiet challenge to the symphony of the solar system that begs us to listen more closely to the notes that aren't being played. This gravitational irregularity is a profound clue about what lies beneath the surface. It suggests that Quaoar is not a simple, homogeneous sphere of mixed ice and rock. Instead, its mass must be distributed in a lopsided or layered way. One compelling possibility is that Quaoar is what scientists call a gravitationally collapsed object. In this scenario, it began as a loose pile of rubble, a collection of smaller bodies that came together gently in the early solar system. Over billions of years, its own gravity would have slowly compressed that material, squeezing it into a more solid form. However, if this process was incomplete or uneven, you could be left with a world that has a dense, compact core but an outer shell that is still somewhat porous and fluffy. This combination would create a gravitational field that doesn't perfectly match the visible shape we see, as the invisible core pulls more strongly than the lighter crust. Another fascinating theory points to a dramatic impact in Quaoar's deep past. A colossal collision could have stripped away a significant portion of its original outer layers, leaving behind a remnant that is much denser than a typical object of its size. Imagine a giant taking a massive bite out of the planet. What remains would be a distorted, irregular body with a gravity field that feels off for its current dimensions. Alternatively, the heat from such a tremendous impact could have caused the heavier rocky material in its center to sink inward in a process called differentiation, while the lighter ices rose to the surface. This would create a planetoid with a very dense, rocky core that is not perfectly centered, making its gravitational pull feel stronger in some directions than others. The most mind-bending possibility, however, involves a hidden internal structure. Quaoar's puzzling gravity could be the strongest evidence yet for a subsurface ocean. If a layer of liquid water exists deep beneath the ice, it would act as a separate, flowing mass within the world. As Quaoar rotates, this liquid interior would slosh and move slightly out of sync with the solid outer shell. This dynamic, shifting mass would constantly alter the subtle tug of gravity measured from orbit, creating the irregularities that so confuse our models. The presence of an ocean would not only explain the gravity anomalies, but also provide a potential source of internal heat and geological activity, tying together several of Quaoar's other mysteries into one revolutionary idea. Adding to its long list of oddities, Quaoar presents us with a landscape that seems to defy the brutal history of our solar system. Across the moon, asteroids, and dwarf planets we've observed, one universal feature is the pockmarked signature of countless impacts, a cosmic battle scar telling a 4-billion-year story of violent collisions. Yet when we train our most powerful telescopes on Quaoar, its surface reveals a startling lack of these massive, basin-forming craters. This is the missing crater paradox. For a resident of the chaotic and crowded Kuiper Belt, Quaoar's face appears surprisingly and suspiciously smooth. It's as if this world has somehow found a way to heal its own wounds, erasing the evidence of ancient impacts through processes we are only beginning to understand. The most immediate and thrilling explanation is that Quaoar is not a dead relic but a geologically active world, one that has experienced widespread resurfacing events in its recent past. On an inert, frozen body, craters accumulate over billions of years like wrinkles on a face, permanently recording every major impact. The only way to remove them is to essentially give the world a new skin. This could be driven by cryovolcanism, where a warm slush of water, ammonia, or methanol erupts from beneath the surface and floods vast regions. Much like lava flows on Earth, bury the old terrain under a fresh, smooth plain. If such eruptions have occurred across Quaoar within the last few 100 million years, a mere blink in geological time, they would have paved over the ancient, cratered landscape, leaving behind the unblemished surface we see today. This would point to a complex and warm interior, fundamentally challenging our notion of these distant objects as simple frozen fossils. Another compelling theory involves a global relaxation of its very crust. Quaoar is composed largely of water ice, which might seem rock solid to us, but on geological timescales and under the gentle, persistent pull of its own gravity, ice can actually behave like a slow-moving fluid. This process, known as viscous relaxation, would cause the steep walls of large craters to gradually slump inward and the deep bowls to slowly rise, effectively causing the crater to slump and fade away over millions of years. The rate at which this happens depends heavily on the temperature and composition of the ice. If Quaoar's icy shell is particularly pure or is kept slightly warm by internal heat, this self-healing process could occur efficiently enough to erase all but the very youngest and largest of impact scars. We must also consider the possibility of a unique form of erosion, unlike anything we see on airless moons like Callisto or our own moon. Perhaps Quaoar's surface is coated in highly volatile ices like nitrogen or methane. Even at these tremendous distances, the faint sunlight could cause these ices to slowly sublimate, transitioning directly from a solid to a gas. Over eons, this gradual loss of material could be sculpting the landscape, smoothing out ridges and filling in depressions in a process called sublimation erosion. It would be an incredibly slow and subtle sandblasting, but given enough time, it could effectively erase the topographic evidence of smaller impacts, leaving behind a softened, gentler terrain. The most radical possibility of all is that we are not looking at Quaoar's original surface at all, but a relatively new one. Quaoar could be what is known as a rubble pile object, a loose collection of smaller rocks and ices held together by gravity. If it suffered a truly catastrophic impact early in its history, one that came perilously close to shattering it completely, the entire world might have been turned inside out. The violence of the collision would have churned the outer layers, burying the old cratered crust deep within and bringing fresh material from the interior to the surface. In this scenario, the face Quaoar shows us today is not the one that endured the early bombardment of the solar system, but a new one that has only been exposed to the comparatively quieter conditions of the more recent cosmic environment. Each of these theories paints a picture of a dynamic and evolving world, one that is actively managing its own appearance against the relentless wear and tear of space. Just when we thought its catalogue of oddities was complete, Quaoar reveals yet another dynamic characteristic. It subtly changes color over time. This isn't a simple shift between two tones, but a slow, mysterious oscillation observed across multiple telescopic observation campaigns. While many objects in the outer solar system possess a somewhat stable coloration, Quaoar's hue appears to fluctuate, suggesting its surface is anything but static. These color variations are a direct signal that chemical or physical processes are actively at work, painting and repainting this distant world in a palette we are only beginning to understand. One of the most plausible explanations for this chromatic dance involves seasonal changes driven by Quaoar's elliptical orbit. As it travels along its path, its distance from the Sun varies significantly. During its closest approach, the slight increase in solar energy, faint as it is, could be enough to trigger the sublimation of the most volatile ices on its surface. Imagine patches of nitrogen or methane ice turning directly from a solid into a gas, wafting away from the surface and leaving behind a different underlying material. This process could expose fresh, brighter water ice or conversely, concentrate darker, complex organic compounds, thereby altering the overall color we perceive from Earth. Then, as Quaoar moves back to the colder, more distant part of its orbit, those gases could recondense as a fresh layer of frost, shifting the color once again in a slow, rhythmic cycle tied directly to its long year. Another compelling theory points to ongoing chemistry on the surface itself. Quaoar is constantly bombarded by cosmic rays and solar radiation, a process known as space weathering. This radiation has enough energy to break apart molecules in the surface ices, a process called radiolysis. Over time, this can create new, more complex compounds known as tholins reddish-brown, tar-like organic molecules that are responsible for the distinct colors of many outer solar system bodies. If this process is occurring unevenly or in pulses, perhaps linked to the solar activity cycle or variations in cosmic ray flux, it could cause the overall color to gradually darken and redden. Conversely, recent impacts could excavate material from beneath this irradiated crust, blasting away the dark tholins to reveal the brighter, less processed ice underneath, causing a temporary whitening of the surface before the radiation once again begins its slow, darkening work. We must also consider the possibility that these color changes are not uniform, but the result of large-scale surface renewal in specific regions. If cryovolcanic activity is indeed occurring, as suggested by other mysteries, an eruption would flood a vast area with fresh, bright material from the interior. This would create a brilliant new spot on the surface, significantly altering the average color of the entire world as seen through our telescopes. Over decades or centuries, that fresh deposit would then darken under the relentless radiation, slowly returning Quaoar to its former shade until the next eruption occurs. This would make the color variations not a global cycle, but a sporadic record of internal geological activity, each shift in hue marking a significant event in the world's recent history. The true intrigue lies in how these color changes compare to other Kuiper Belt objects. Many of Quaoar's neighbors show remarkably stable colors, their surfaces having reached a sort of chemical equilibrium after billions of years of radiation. The fact that Quaoar is still actively changing suggests it is somehow different. Perhaps its unique composition makes its surface chemistry more sensitive, or its internal activity provides a constant source of new material that resists reaching that final, stable state. Its changing color is a visible manifestation of its dynamic nature, a clear sign that this is not a dead world but a surprisingly active one, continuing to evolve right before our eyes, even from across the vast expanse of the solar system. Diving deeper into the heart of this enigmatic world, we encounter a problem that strikes at the very core of how we understand it. The numbers simply don't add up. Astronomers have employed multiple, independent methods to calculate Quaoar's density, a fundamental property that tells us what this world is truly made of. But instead of converging on a single answer, these techniques have produced a confounding spread of values, a clear and puzzling discrepancy that forces us to question whether we're misreading the data, or if Quaoar itself is hiding a radical secret within its structure. To understand why this is such a dilemma, we need to grasp what density represents. In simple terms, an object's density is its mass divided by its volume. It's a measure of how much stuff is packed into a given space. For a distant world like Quaoar, we can't just put it on a scale or dunk it in a measuring cup. We have to be clever. One primary method for determining its mass involves studying the orbit of its moon, Weywot. By carefully tracking the precise gravitational dance between the two bodies, we can calculate the strength of Quaoar's pull, which directly reveals its mass. This technique is a cornerstone of astronomy and is generally considered extremely reliable. Figuring out its volume, however, is a different challenge. We need to know its exact size, which requires measuring its diameter. This is often done by observing moments when Quaoar passes in front of a distant star, an event called a stellar occultation. By timing how long the star's light is blocked, we can get a remarkably accurate measurement of the world's width. When you take the mass from the first method and plug it into the volume from the second, you should get a clear, consistent density. But for Quaoar, this calculated density often ends up surprisingly high, suggesting a composition dominated by rock with only a small fraction of ice. Here's where the conflict arises. Another powerful technique called thermophysical modeling paints a very different picture. This method involves studying the heat radiating from Quaoar's surface. The amount of thermal energy an object emits is intimately tied to its size and its albedo, or reflectivity. By carefully measuring its infrared signature, scientists can work backwards to estimate its diameter. The diameters derived from these thermal models are frequently larger than those measured by stellar occultations. A larger volume, when combined with the same mass from Weywot's orbit, results in a significantly lower calculated density. This value points to a world that is much less compact, perhaps a mix of nearly equal parts rock and ice. So we are left with two reputable scientific methods yielding two different realities, one of a dense, rocky world and another of a lighter, icier body. This discrepancy is far more than a minor accounting error. It's a direct clue that something is unusual about Quaoar. One possibility is that our measurements are being tricked by the object's physical properties. For instance, the thermophysical model assumes Quaoar has a relatively smooth surface, but if its terrain is incredibly rough and porous, filled with deep, shadowy craters, it would emit heat less efficiently. To explain the amount of heat we detect, we would have to assume the object is larger than it actually is, leading to an overestimation of its diameter and an underestimation of its density. The occultation method, on the other hand, could be thrown off if Quaoar isn't a perfect sphere. If it has a slightly elongated or irregular shape, different occultation events might measure different chords across the object, leading to an incomplete picture of its true average diameter. The most thrilling explanation, however, is that the discrepancy is real and points to a bizarre internal structure. Quaoar may not be a uniform blend of rock and ice. It could have a wildly lopsided mass distribution, perhaps due to a gargantuan impact that stripped away much of its outer, lighter layers and left behind a dense, rocky core that is not centered within its overall form. This would mean its gravitational pull, which we use to find its mass, is dominated by this hidden, concentrated core, while its physical size is defined by its outer shell. We would be measuring two different aspects of the same object, creating the illusion of conflicting densities. Alternatively, Quaoar could be a rubble pile world with a cavernous interior, a collection of large boulders and ice chunks with significant empty space between them. Its mass would be straightforward, but its effective volume would be enormous, resulting in a very low overall density that doesn't match our expectations for a solid body. This density dilemma forces us to consider that Quaoar might be less a single, cohesive planetoid and more a loosely bound puzzle of fragments, holding its shape through gravity alone while hiding vast voids within. Even as we attempt to map its surface from afar, Quaoar's own light reveals yet another layer of strangeness in the form of its unusual light curve. When astronomers measure the brightness of a distant object over time, they typically see a smooth, predictable pattern, a gentle rise and fall that corresponds to the rotation of a mostly spherical body, perhaps with a dark patch or a bright region creating a small, consistent hump in the data. Quaoar's light curve, however, is anything but smooth. It displays pronounced asymmetries, sharp dips, and irregular bumps that deviate dramatically from the expected pattern of a simple, rotating sphere. These anomalies are a clear signal that we are not looking at a typical world. Something about its shape, its surface, or its environment is deeply unconventional. One of the most straightforward explanations for these irregularities is extreme surface topography. We are likely not dealing with a bland, gently rolling landscape. Instead, Quaoar could be shaped by dramatic and unique geological features. Imagine a single, colossal mountain range or a vast, deep basin that stretches across a significant portion of its hemisphere. As this world rotates, such a massive feature would first obscure, then reveal, a different amount of surface area to our line of sight, creating a distinct and asymmetric kink in its light curve. Alternatively, Quaoar's overall shape might be profoundly irregular, perhaps elongated or even slightly squashed like a potato. The changing cross-section of an oddly shaped body tumbling through space would naturally produce a complex pattern of brightening and dimming that defies the simple model of a perfect sphere. Another compelling possibility points to wild variations in surface albedo or reflectivity. Rather than its shape, it could be the patchwork nature of its surface that is causing the strange light patterns. Picture a world where a single hemisphere is dominated by a vast, brilliant plain of freshwater ice, reflecting sunlight like a cosmic mirror, while the opposite hemisphere is a sprawling, dark field of complex organic tholins, absorbing most of the light that hits it. If the boundary between these two extremes is not aligned with its equator or poles, the transition between the bright and dark sides during rotation would not be a smooth gradient but a jarring, sudden shift in overall brightness. This could easily account for the sharp spikes and dips observed in the data, painting a picture of a world with a surface of stark and dramatic contrast. We must also seriously consider that the anomalies are not coming from Quaoar alone. The peculiar features in the light curve could be the signature of previously undetected companion objects. While Weywot is its known moon, there could be other, smaller bodies lurking in the system. A faint, close-orbiting satellite, too small and dark to be seen directly, could be periodically passing in front of or behind Quaoar from our perspective, casting a tiny shadow or adding its own minuscule bit of reflected light to the total signal. Even a tenuous, dusty ring that is denser in certain arcs than others could create subtle, repeating dimming events as it rotates, adding another complex layer to the light curve. Each of these scenarios suggests that Quaoar's system is more complex and populated than it appears, a miniature planetary system with its own hidden members. The most tantalizing possibility of all is that we are seeing the combined effect of all these factors. A world that is simultaneously irregularly shaped, patchily colored, and surrounded by a faint, structured ring of debris. This would create a light curve of such profound complexity that untangling its individual contributors becomes a monumental challenge. These anomalies are not merely noise in the data, they are a precise, if cryptic, language. Decoding the specific timing, depth, and shape of each dip and peak in Quaoar's light is our best tool for remotely mapping its topography and surface composition, offering a glimpse into the true nature of this deeply puzzling world without ever needing to leave our own planet. If the mere presence of methane on Quaoar was a puzzle, its specific arrangement on the surface presents an even deeper conundrum. Detailed spectroscopic maps don't show a uniform blanket of this volatile ice. Instead, they reveal a bizarrely patchy and uneven distribution. Methane appears concentrated in specific, isolated regions, while vast areas seem curiously devoid of it. This isn't what we'd expect for a simple, frozen world. On an inert body, a substance like methane should either be globally present, having settled evenly over eons, or completely absent, having long since escaped into space. The fact that it exists in these strange, selective pockets suggests that powerful and dynamic forces are actively at work, managing and moving this precious volatile compound across the landscape in a complex cycle we are only beginning to decipher. One of the most compelling theories to explain this patchwork is a process of seasonal migration, a slow-motion journey driven by the faint warmth of the distant sun. Quaoar's orbit is noticeably elliptical, meaning its distance from the sun changes significantly over its 288-year-long journey. During its closest approach, or perihelion, the slight increase in solar energy, minuscule as it is, might be just enough to warm specific sun-facing slopes and equatorial regions above the sublimation point for methane. In these areas, the solid ice would transform directly into a gas, creating an incredibly tenuous, temporary atmospheric haze. This methane gas wouldn't simply vanish. Prevailing micro-winds or pressure differences could carry it across the globe until it reaches colder, more sheltered regions, perhaps deep polar craters that never see the sun, or areas currently experiencing their long winter night. There, the gas would condense and refreeze, falling as a fine methane snow and creating a fresh, bright deposit. Over centuries, this could create a constantly shifting map of methane ice, with it accumulating in cold traps and vanishing from warmer zones, explaining the stark contrasts we observe from Earth. Another fascinating possibility involves chemistry rather than physics. The distribution we see might not be methane ice at all, but rather the visible signature of ongoing chemical reactions. Quaoar's surface is constantly bombarded by radiation, which can break apart methane molecules and reassemble them into more complex hydrocarbons and tholins. It's possible that certain areas of the surface have a catalyst present, perhaps a specific mineral or a different type of ice, that dramatically accelerates this process. In these active zones, any methane that appears will be quickly processed and transformed into a different, darker substance, preventing it from building up a visible reservoir. In other, more inert regions, the methane could persist for much longer, creating the observed patches of relatively pure ice. The uneven landscape wouldn't be a result of migration, but a testament to the varied chemical reactivity of the terrain itself. We must also consider the role of geology as a master gardener, cultivating methane in some places and not others. If cryovolcanism is real on Quaoar, these icy volcanoes would act as direct pipelines from a potentially methane-rich interior. An eruption would not only spew water ice but could also bring fresh methane to the surface, depositing it in a concentrated plume around the vent and creating a bright, localized patch. Conversely, tectonic activity could play a part. Cracks and faults in the crust could allow subsurface methane to slowly seep out, outgassing in specific linear features or calderas rather than across the entire globe. The patchy distribution would then be a direct map of the world's most geologically active regions, highlighting where its internal workings are breaching the surface. An even more external influence could be at play, the protective shadow of its own moon, Weywot. While small, the moon's orbit could cast a moving shadow across Quaoar's surface. Over millennia, this consistent shading could create permanently colder regions that have acted as preferential cold traps, selectively collecting and preserving methane ice that was lost from the more frequently sunlit areas. It's a subtle gravitational partnership that extends beyond mere tides, with Weywot literally drawing a curtain against the sun to preserve these volatile deposits. Each theory, from seasonal journeys to chemical factories and geological vents, paints a picture of a world that is far from a static ice ball. The uneven spread of methane is a powerful clue that Quaoar is a dynamic and ever-changing environment, its surface a constantly shifting canvas upon which the fundamental processes of physics, chemistry, and geology are actively writing their story. As if its independent orbit wasn't puzzling enough, Quaoar throws another curveball with the very angle of its path. While most large objects in the Kuiper Belt orbit the Sun in a relatively flat disk, much like the planets, Quaoar's path is dramatically tilted. Its orbital inclination of about 8 degrees may sound small, but in the context of the outer solar system's orderly plane, this is a significant and unusual tilt. For a world of its size, this high inclination is an anomaly, a clear sign that its past was anything but peaceful and orderly. It prompts a fundamental question: what powerful force could have knocked Quaoar so decisively out of the solar system's primary plane? The most likely culprit is a gravitational encounter, a cosmic bump that altered its course billions of years ago. The leading model of our early solar system describes a period of profound chaos, a gravitational pinball game where the giant planets, particularly Neptune, migrated outward. As Neptune moved, its immense gravity would have acted like a plow, scattering countless icy bodies. A close pass from the young Neptune could have easily given Quaoar a powerful gravitational kick, lifting its orbit to the inclined path we see today. This scenario would neatly link its tilt to the same great migration that shaped the orbits of so many other Kuiper Belt objects, placing Quaoar's story within a broader narrative of solar system evolution. However, there's an alternative and even more dramatic possibility: that Quaoar's inclination is not a scar from Neptune, but a signature of a much more distant origin. Some scientists speculate that it could be a captured object that originated not in the classical Kuiper Belt, but from the scattered disk, a more distant and chaotic region of icy bodies with wildly inclined and eccentric orbits. In this case, a complex interaction with another large, yet undiscovered object in the far reaches of the solar system could have altered its path, sending it inward until it was gently captured into its current orbit by Neptune's gravity. This would make Quaoar an immigrant from the solar system's outermost frontier, a visitor from a region we are only beginning to explore. A third, and perhaps most profound, theory looks not outwards but inwards to the very beginning. What if Quaoar's inclined orbit is not an anomaly at all, but a primordial relic? The early protoplanetary disk from which all planets formed may not have been perfectly smooth. It could have had waves, lumps, and local gravitational instabilities. It's possible that Quaoar formed in a part of the disk that was already slightly tilted, and it has maintained that original inclination ever since, a frozen record of the solar system's messy and turbulent birth. If true, this would make it a rare time capsule, preserving a configuration that was erased for most other large bodies through collisions and gravitational smoothing. Each explanation offers a different glimpse into the violent and dynamic processes that built our cosmic neighborhood, with Quaoar's tilted path serving as a permanent monument to that ancient chaos. This brings us to a fundamental geological mystery: just how old is Quaoar's skin? When astronomers study a world, one of their primary goals is to date its surface, to read the history written in its craters and plains. For most airless bodies in the solar system, this is a straightforward process. Surfaces are ancient, dating back billions of years to the era of heavy bombardment, and their age is directly proportional to the number of impact craters that scar them. More craters mean an older surface, fewer craters indicate a younger one that has been resurfaced. But when we apply this simple logic to Quaoar, the story completely falls apart. The evidence is utterly contradictory, presenting a surface that somehow manages to look both impossibly ancient and startlingly young at the very same time. On one hand, vast regions of Quaoar appear to be primordial, bearing the heavy scars one would expect from a 4.5 billion year existence in the chaotic Kuiper Belt. These areas are densely cratered, a testament to a long and violent history of impacts that have left their permanent mark. This is the surface we expect to see, a frozen record of the solar system's earliest and most violent epochs. Yet, right alongside these ancient terrains, we find enormous expanses that are almost suspiciously smooth, with a glaring and profound lack of large craters. These plains are so unblemished that they cannot possibly be as old as the solar system itself. It's the geological equivalent of finding a pristine, freshly paved highway running directly through the middle of a weathered, ancient ruin. The two landscapes simply do not belong together in the same time period. This contradiction forces a radical conclusion. Quaoar must be geologically active, possessing some powerful mechanism that is continually erasing the evidence of impacts and renewing its face, even in the deep freeze of space. But what process could possibly achieve this renewal so far from the sun's warmth? The most captivating explanation is widespread cryovolcanism. Imagine not the fiery, rock-based volcanoes of Earth, but their icy counterparts. Deep within Quaoar, a combination of heat from radioactive decay and gravitational tidal forces from its moon could maintain a layer of liquid water, a subsurface ocean rich in ammonia or salts that act as a potent antifreeze. This warm slush under pressure would occasionally find a weakness in the overlying icy crust and erupt onto the surface. When it does, it would flood the surrounding landscape, not with lava, but with a slurry of water, ammonia, and methanol that quickly freezes into a brilliant, smooth plain of new ice. This single event would instantly wipe away all previous craters in that area, resetting the geological clock to zero. If such eruptions have happened sporadically across different regions over billions of years, it would perfectly explain the bizarre patchwork of old and new terrain we observe. Another potential surface renewal agent is the slow but relentless flow of ice itself. Water ice, though solid to our touch, can behave like a viscous fluid over geological timescales, especially when slightly warmed. If Quaoar's interior provides even a faint trickle of heat, its thick icy crust could very slowly flow and ooze, much like a glacier on Earth. This glacial flow would gradually fill in and soften craters, causing the sharp rims to slump and the deep bowls to rise, effectively erasing them from the landscape over millions of years. The process would be incredibly slow, but given the vast eons of time available, it could efficiently smooth over large portions of the world, maintaining a deceptively youthful appearance. We must also consider a more exotic form of erosion unique to these frozen realms: sublimation-driven landscaping. Even at these tremendous distances, the faint sunlight can cause the most volatile ices on Quaoar's surface, like nitrogen or methane, to slowly turn directly from a solid into a gas. Over hundreds of millions of years, this gradual loss of material would act like a subtle but persistent sandblaster, smoothing down topographic features and subtly altering the landscape. While it might not erase large craters completely, it could effectively soften their edges and infill their bases, contributing to a younger-looking appearance. This process would be highly dependent on the local composition, potentially explaining why some regions appear older than others. Areas rich in water ice would remain stable, while patches of volatile ices would slowly fade and reform. The most astonishing implication of this age controversy is that it shatters our long-held assumption that small, distant worlds are necessarily dead and geologically static. Quaoar is forcing us to accept that geological activity is not solely the domain of planets. A combination of internal heat, unusual chemistry, and the peculiar physical properties of ice can grant even a small Kuiper Belt object a dynamic and evolving geology, capable of renewing itself against the relentless wear of time. Its surface is a palimpsest, a parchment on which the original ancient text is still visible in places, but which has been scraped clean and rewritten in others, telling a complex story of a world that is very much alive. But the gravitational intrigue surrounding Quaoar extends far beyond its relationship with Neptune, reaching into a much more chaotic and sparsely populated region of our solar system. To truly appreciate the next mystery, we need to venture into the scattered disk. This vast, diffuse cloud of icy bodies represents the outer frontier of the Kuiper Belt, a population of objects whose wild, elongated orbits are a direct result of violent gravitational encounters with Neptune in the distant past. These are the solar system's scattered souls, flung into highly eccentric and inclined paths by the migrating giant planet. Given its substantial size and location, conventional wisdom suggests Quaoar itself should bear the unmistakable scars of this ancient turmoil. A world this massive acts as a gravitational anchor, a beacon that should have attracted countless close passes from these wandering scattered disk objects over billions of years. Each near miss would have subtly tugged at Quaoar, potentially altering its own orbit or leaving behind a spray of impact craters. Yet, when we observe it, Quaoar appears remarkably serene and relatively undisturbed. Its orbit is stable, its surface, while complex, doesn't show the extreme cratering one might expect from such a violent neighborhood. It's as if the chaotic dance of the scattered disk happened all around it, but Quaoar itself was somehow spared, standing untouched in the eye of a gravitational hurricane. This pristine condition presents a profound puzzle. How could such a large target avoid the relentless bombardment and gravitational nudging that defines its entire region? One compelling theory is that Quaoar is a relative newcomer to its current address. Perhaps it did not form in its present location within the main Kuiper Belt at all, but instead originated much closer to the Sun. According to this idea, Quaoar could have been gently nudized into its current stable orbit during the final stages of planetary migration, arriving after the most intense period of scattering had already concluded. In this scenario, it slipped into a quiet orbital niche that had already been cleared of the majority of potential impactors, like moving into a house after the neighborhood's rowdy founding party was already over. This would explain its lack of disruption. It simply wasn't there to experience the worst of the chaos. Another fascinating possibility is that Quaoar possesses a unique gravitational signature that naturally protects it. Its specific orbital parameters, its exact distance from the Sun, its eccentricity, and its inclination might place it in a kind of gravitational safe zone, a stable pocket within the broader chaos of the scattered disk environment. Certain orbital resonances, even weak or temporary ones, could act as protective barriers, deflecting incoming scattered objects away from a direct collision course. It could be the beneficiary of a delicate and fortunate celestial balancing act, its path perfectly tuned to avoid the most common trajectories of its erratic neighbors. We must also consider the nature of the interactions themselves. The scattering events that sent these objects on their wild paths happened primarily billions of years in the past. The scattered disk population we see today is just a remnant of that initial chaotic exodus. It's possible that the current density of potential impactors is simply far lower than we traditionally estimate, making catastrophic collisions or significant orbital perturbations exceptionally rare events, even over astronomical timescales. Quaoar's peaceful existence might not be an anomaly, but rather the normal state for objects of its size in that region, suggesting our models of the scattered disk's population and dynamics need refinement. Perhaps the most thrilling explanation is that Quaoar hasn't been untouched at all, but has a remarkable ability to heal its wounds. As we've explored with other mysteries, evidence suggests this world may be geologically active. Widespread cryovolcanism or glacial flow could be continuously resurfacing the planet, erasing the craters from those inevitable impacts almost as soon as they form. From this perspective, the lack of obvious disruption isn't because impacts aren't happening, but because Quaoar is actively healing itself, maintaining a deceptively youthful facade that hides a violent history. Its serenity is not a sign of a quiet life, but of an incredibly resilient constitution. This interaction, or lack thereof, with the scattered disk forces us to reconsider the history of our solar system's outer reaches and the surprising resilience of some of its most distant worlds. Yet for all its intrigue, the relationship between Quaoar and its lone known moon, Weywot, is itself shrouded in a fundamental uncertainty that strikes at the very core of how we define this system. Could Weywot truly be its only companion, or are we looking at something far more complex? This brings us to a compelling debate that has quietly simmered among planetary scientists: the possibility that Quaoar is not a single body with a moon, but is in fact a binary system, or perhaps even hosts a hidden retinue of additional, unseen satellites. The gravitational evidence we have is both tantalizing and frustratingly ambiguous, offering clues that could point in multiple directions and forcing us to reconsider the basic architecture of this distant world. The case for a binary system primarily hinges on the significant size of Weywot relative to its parent body. While we lack precise measurements, initial estimates suggest Weywot could be as large as 170 kilometers in diameter. When a moon is this substantial compared to the world it orbits, the gravitational center of their mutual dance, known as the barycenter, shifts. Instead of lying deep within Quaoar, it could potentially reside in the empty space between them. This is the defining characteristic of a binary system, where two worlds essentially orbit each other around a shared point of balance. Pluto and its largest moon, Charon, are the classic example of this. Their barycenter is in the void between them, officially making Pluto a binary dwarf planet. The gravitational interplay between Quaoar and Weywot shows subtle anomalies that could be interpreted as a hint of this very phenomenon, suggesting their partnership might be far more equal than the traditional planet and moon model implies. If true, this would dramatically elevate Weywot's status from a mere satellite to a co-dominant component of a truly dual-world system. However, the evidence is far from conclusive, and a strong counterargument exists. Precise tracking of Weywot's orbit reveals a path that, while stable, shows slight irregularities that are difficult to explain if it is the only significant gravitational player in the system. These tiny wobbles and orbital residuals could be the signature of other, much smaller moons exerting their own faint gravitational tugs. The gravitational pull required to create these minute disturbances wouldn't need to come from another large body. It could be the collective influence of several tiny, kilometer-sized moonlets, too small and dark for our current telescopes to directly image. These hidden shepherds could be orbiting closer in or further out, their combined gravity gently perturbing Weywot's path in a way that masquerades as a more complex binary interaction. In this scenario, Quaoar wouldn't be a binary but a more traditional planetary system in miniature, with a central primary body and a small family of moons. The search for these elusive additional moons has been intensive, yet so far every dedicated observation campaign has come up empty. This absence of direct visual evidence is paradoxically another piece of the puzzle. It doesn't rule out their existence, it merely tells us that if they are there, they must be exceptionally faint. They could be composed of incredibly dark material, or more likely, they are simply too small to reflect enough sunlight for detection across billions of miles of space. Their potential existence isn't just an academic curiosity. It could provide the missing key to other Quaoar mysteries. Such moonlets could be the invisible shepherds responsible for confining the particles of its mysterious ring, their tiny gravitational nudges providing the structure needed to prevent the debris from coalescing into a single moon. The very stability of that impossible ring might be the strongest indirect evidence we have for a hidden population of satellites. Ultimately, the binary question forces a deeper philosophical issue about how we classify the complex gravitational relationships that exist in the outer solar system. The line between a binary system and a planet with a large moon is often blurry, defined by a precise mathematical calculation of where the barycenter lies. Until we can get more precise data on the masses of both Quaoar and Weywot, a definitive answer remains just out of reach. This ongoing debate highlights a beautiful truth about modern astronomy. Even with our most powerful instruments, some of the solar system's most basic questions, how many worlds orbit this sun, and how they interact, are still open for discovery, waiting for a sharper image or a more precise measurement to reveal the truth hidden in the darkness. Yet another layer to this reflective enigma involves the potential for shadow hiding, an effect that depends heavily on surface texture. On a world with a very rough and porous surface, like one covered in a deep layer of icy froth or sharp, jagged terrain, sunlight would not reflect in a single, coherent way. Instead, it would scatter into countless tiny shadows created by the microscopic peaks and valleys. This would make the surface appear uniformly dark from most angles as the light gets trapped and absorbed in the miniature canyons. However, when Quaoar is at a specific alignment in its orbit known as opposition, where the sun is directly behind the observer, a dramatic brightening can occur. This opposition surge happens because all those tiny shadows are hidden from view, instantly revealing the true, brighter reflectivity of the ice itself. If Quaoar's surface is uniquely textured, this surge could be far more pronounced than on smoother objects, creating a distinctive reflective signature that changes dramatically based solely on our viewing angle. We must also consider the possibility of a transient contributor to this reflective puzzle, the fleeting presence of a temporary atmosphere. While Quaoar seems to lack a permanent gaseous shroud, it's possible that when its elliptical orbit brings it closest to the sun, the faintest whisper of an atmosphere could briefly emerge. The most volatile ices on its surface, like nitrogen or carbon monoxide, might sublimate for a short period, creating an extremely tenuous haze of gas. Even a vanishingly thin atmosphere like this would act as a diffuse screen of fine particles suspended above the surface. Sunlight striking this haze would scatter in every direction, a phenomenon known as Rayleigh scattering. This would not only make the entire world appear slightly brighter to our telescopes, but could also impart a subtle, uniform glow that smooths out the contrasts between dark and light regions on the ground, effectively altering its overall reflective profile for a short time before the gases inevitably collapse back into frost. Ultimately, Quaoar's unusual reflectivity is a powerful composite clue. It isn't the result of one single factor, but likely a complex interplay of its unique chemical recipe, its potentially frothy and rugged physical texture, and perhaps even fleeting atmospheric events. This distinctive way of handling light makes it a true outlier among its peers, a world that doesn't play by the same reflective rules as other Kuiper Belt objects. By studying this peculiar glow, we aren't just learning about what covers its surface. We are gaining profound insights into the active and diverse processes that continue to shape this distant, dynamic world billions of miles from the sun. Just when we think we have a handle on Quaoar's place in the grand chronology of our solar system, its very age throws us another curveball. The story of our cosmic neighborhood's formation is one we've pieced together with remarkable confidence, a timeline where the Sun, ignited around 4.6 billion years ago, followed swiftly by the rapid coalescence of planets from the swirling protoplanetary disk within the first 100 million years. The Kuiper Belt is understood to be a remnant of that early era, a population of ancient leftovers that never managed to accrete into a full-fledged planet. Most of its members are expected to be primordial, dating back to the very dawn of the solar system. Quaoar, however, refuses to fit neatly into this timeline. Different lines of evidence point to wildly different birthdays for this world, creating a profound contradiction that forces us to question not just its own history, but the very sequence of events that built the outer solar system. One set of clues seems to argue for an incredibly ancient origin. The heavily cratered regions on its surface, what we can see of them, speak of a landscape that has endured billions of years of bombardment. The sheer density of impacts in these areas suggests a surface that has been exposed to the violent chaos of the early solar system for an immensely long time, a hallmark of a truly primordial object. Furthermore, its current stable orbit, while unusual, appears to be well settled, as if it has occupied this particular path for eons, weathering the gravitational storms of planetary migration without being completely disrupted. This evidence paints a picture of Quaoar as a senior citizen of the Kuiper Belt, a first-generation planetesimal that formed alongside the building blocks of the planets and has remained a frozen witness to the entirety of solar system history. Yet, other evidence strongly suggests a much younger, more dynamic world, one that cannot possibly be that old. The existence of its massive ring system is a huge problem for an ancient age. Without a continuous replenishment mechanism or some unknown stabilizing force, that ring should have coalesced into a moon within a tiny fraction of the solar system's lifespan, perhaps within just a few decades or centuries. Its continued presence is a screaming anomaly that suggests either the ring is a very recent feature, the result of a catastrophic collision that occurred in the relatively recent past, or our fundamental understanding of orbital mechanics in such environments is deeply flawed. Adding to this is the startling youthfulness of its smooth, resurfaced plains. Geological features don't remain pristine for billions of years, they are worn down by impact. The existence of these vast, unblemished regions implies a powerful resurfacing event, or a series of them, that occurred long after the heavy bombardment period ended, perhaps within the last billion years. A world cannot be both 4.6 billion years old and have a brand new face. The two ideas are mutually exclusive. This contradiction forces astronomers to consider extraordinary possibilities for Quaoar's formation. One radical theory is that it is indeed a primordial body, but one that was completely shattered in a gargantuan collision relatively recently in its history. This catastrophic event would have torn the original Quaoar apart, only for its fragments to slowly reaccrete under gravity into the world we see today. In this scenario, Quaoar is both old and young. Its constituent materials are ancient, but its current form is a modern reconstruction. This would explain the young surface and the potential for a recent ring-forming event, while its overall composition would still reflect its ancient origins. It would be a phoenix rising from its own icy ashes. An alternative, equally mind-bending idea is that Quaoar is not a native of the Kuiper Belt at all, but an immigrant captured from a much more distant population. Some models suggest that a vast reservoir of icy bodies exists in the far outer reaches of the solar system, far beyond the Kuiper Belt in a region known as the Weywot cloud. The gravitational influence of a passing star could have perturbed one of these objects, sending it on a journey inward where it was gently captured by the Sun's gravity and settled into its current orbit. If true, Quaoar could be significantly younger or older than the typical Kuiper Belt object, representing a different population with a completely different formation history. Its contradictory clues would then make perfect sense, as they would be telling the story of its original home, not its current neighborhood. This formation timeline puzzle is far more than an academic debate about a single world's birthday. It strikes at the heart of our planetary origin story. If Quaoar is a reassembled rubble pile, it tells us that catastrophic collisions continue to reshape large bodies in the Kuiper Belt for much longer than we believed, implying a far more violent and dynamic recent history in this distant region. If it is a captured interstellar immigrant, it provides our first tangible evidence of the material that makes up the inner Weywot cloud, offering a priceless sample of the very edges of our solar system's influence without having to send a probe on a millennia-long journey. Quaoar's contradictory age is a cosmic riddle that challenges the clean narrative we've constructed, reminding us that the history of our solar system is likely far more complex, violent, and interconnected than we ever imagined. As we pull our focus back from Quaoar itself and look at its place among the other giants of the Kuiper Belt, a fascinating and mysterious connection emerges, one that links it to one of the most bizarre objects in our solar system, the dwarf planet Haumea. At first glance, these two worlds appear quite different. Haumea is famous for its incredible speed, spinning so fast it has been stretched into the shape of an elongated ellipsoid like a cosmic football. Quaoar, by contrast, rotates at a much more leisurely pace. Yet, when we look closer, a series of uncanny similarities in their orbits and their very composition begin to surface, suggesting a hidden relationship that has astronomers questioning whether we are looking at long-lost siblings or just two products of the same chaotic environment. The first and perhaps most compelling clue lies in the paths they trace around the Sun. Both Quaoar and Haumea occupy orbits that are significantly tilted compared to the general plane of the Kuiper Belt. This shared high inclination is a major red flag. In the context of solar system dynamics, objects that share similar orbital characteristics, especially unusual ones like this, often share a common history. It strongly suggests that both were subjected to the same powerful gravitational influences billions of years ago, most likely during the Great Migration of Neptune. Their tilted paths could be permanent scars from a series of close encounters with the giant planet, which knocked them both out of the primordial disk and into their current elevated orbits. This shared experience points to a possible common origin in a specific region of the early solar system, a neighborhood that was particularly affected by the shifting gravitational tides. But the connection runs deeper than just their orbits. Spectroscopic analysis reveals a surprising compositional kinship. Both Quaoar and Haumea have surfaces dominated by crystalline water ice. As we discussed earlier, this is a significant detail because crystalline ice requires an energy source to form and maintain its structured state. It doesn't last long in the frigid, radiation-bathed environment of the Kuiper Belt without being refreshed. The presence of this fresh, bright ice on both worlds is a powerful indicator that they have both experienced significant internal heating and resurfacing events in their geologically recent past. This could mean they both possess, or once possessed, warm interiors powered by radioactive decay, or that they both experienced massive collisions that generated enough heat to melt and recrystallize their surface ice on a global scale. This last point, the possibility of colossal impacts, is where the mystery takes a thrilling turn. Haumea is not alone. It is the central figure in a unique family of objects. Astronomers have identified dozens of smaller Kuiper Belt objects that share its orbital characteristics and its unique, bright, icy composition. The prevailing theory is that these are all fragments from a single, titanic impact that shattered a larger proto-Haumea billions of years ago. The force of the collision was so immense it created the fragments, spun Haumea up to its incredible rotational speed, and coated everything in a layer of fresh ice. So, could Quaoar be a part of this same family? Could it be a larger fragment from that same ancient catastrophe? Its compositional similarities make it a candidate, but its very different rotation and lack of a similar retinue of associated fragments make it an outlier. Perhaps it wasn't a fragment, but the impactor itself, the other half of the colossal crash that created the Haumea family. In this scenario, Quaoar would be the surviving rogue body that struck Haumea and careened away on its own unique path, forever linked to the destruction it caused. Alternatively, Quaoar and Haumea might not be direct relatives, but instead represent a previously unrecognized class of Kuiper Belt object. Their shared properties, the crystalline ice, the evidence of past activity, the inclined orbits might be the hallmark of a specific type of large, differentiated world that formed in a particular region of the early solar nebula, one that was rich in the radioactive elements needed to power internal geology. They could be the sole surviving examples of a group of planets that were mostly destroyed during the chaotic early eons, making them rare and precious windows into a lost chapter of our solar system's formation. Unraveling the true nature of their connection is more than just genealogy. It is a direct line of inquiry into the most violent and formative processes that built the outer solar system and determined the fates of its countless inhabitants. But as we attempt to peer beneath its perplexing surface, we are confronted with a foundational uncertainty that underpins nearly every other mystery. What is Quaoar actually like on the inside? This brings us to one of the most fundamental and unresolved puzzles of all. Scientists are locked in a quiet but intense debate over the world's internal structure, with two completely opposing models vying for dominance. On one side, we have the theory of a fully differentiated interior, a world that has separated into distinct layers like a cosmic onion. In this scenario, the heaviest materials, primarily rock and metal, sank to the center under the relentless pull of gravity billions of years ago, forming a dense, compact core. This would be surrounded by a thick mantle of solid but relatively soft water ice, which might itself encase a hidden, slushy ocean kept liquid by antifreeze compounds like ammonia. Finally, the whole structure would be topped with a brittle, frozen crust of more complex ices and organic tholins. This layered model elegantly explains several of Quaoar's other mysteries. A dense, metallic core would account for the higher density estimates and the peculiarities in its gravitational field. A subsurface ocean could be the engine for cryovolcanic resurfacing, erasing craters and creating young plains, while also providing the internal heat that might explain its anomalous thermal readings. Yet, a compelling counterargument exists for a completely different internal reality, a homogeneous or undifferentiated structure. In this model, Quaoar is a primitive and pristine relic, a frozen fossil that never experienced the internal heating necessary to cook its ingredients. Instead of settling into neat layers, the rock and ice remain thoroughly mixed together from crust to core, like a poorly blended cosmic fruitcake. This primordial mixture would have a much lower overall density, aligning with the estimates derived from thermal modeling. It would also present a far more static and inert picture of the world, suggesting its surface features are not the product of internal geology, but of external processes like impacts and sublimation. A homogeneous Quaoar would be a simpler, colder, and deader world, its story written entirely by outside forces rather than an active internal engine. So why can't we simply choose between these two radically different visions? The answer lies in the agonizingly limited data we have to work with. We cannot drill into Quaoar. We cannot send a seismic wave through it to listen for its internal echoes. Our only clues are indirect and frustratingly ambiguous. The conflicting density measurements we discussed earlier lie at the very heart of this conundrum. If the higher density values from orbital dynamics are correct, they strongly favor a differentiated structure with a hefty rocky core. If the lower densities from thermal models are more accurate, they point toward a more uniform mix of ice and rock. Until we can resolve which measurement is truly right or understand why they disagree, the internal blueprint remains a guessing game. Furthermore, the presence or absence of certain molecules on the surface adds another layer of complexity. The detection of crystalline water ice, which requires energy to form and maintain, is a tantalizing hint of internal heat and possibly differentiation. However, it's not definitive proof. A massive impact could have provided the necessary energy to crystallize the ice locally without the entire world differentiating. The potential presence of ammonia hydrate is another critical clue, as ammonia acts as a powerful antifreeze that could enable a subsurface ocean to exist even within a largely cold and undifferentiated body, blurring the lines between the two models entirely. This fundamental uncertainty about its internal architecture means that every other mystery we explore is built on shifting ground. We cannot fully understand its geology, its thermal anomalies, or its potential for habitability until we solve this most basic of puzzles. Is Quaoar a complex, layered world with a fiery past, or a simple, frozen time capsule from the dawn of the solar system? The answer is the master key that would unlock the truth of this distant enigma. The concept of seasons on a world 4 billion miles from the Sun might seem like a contradiction, a phenomenon reserved for planets with significant axial tilts and substantial atmospheres. Yet for Quaoar, the question of seasons is not one of simple presence or absence, but a complex puzzle of how such cycles could possibly operate in the deep freeze of the Kuiper Belt. With an orbital period of 288 years, a single Quaoar year is longer than the entire lifespan of the United States as a nation. Within this immense time frame, the subtle gravitational and radiative forces at play could indeed trigger changes that, while imperceptible to an human eye, would represent a form of seasonality unique to this distant realm. The primary driver of any potential season on Quaoar would be its significantly elliptical orbit. Its path around the Sun is not a neat circle but a stretched oval, meaning its distance from the solar furnace varies dramatically. At its closest approach, or perihelion, Quaoar ventures to within roughly 41 astronomical units of the Sun. At its most distant point, aphelion, it retreats to almost 45 astronomical units. This 4 astronomical unit difference might not sound like much, but in the energy-starved outer solar system, it represents a substantial variation in the minuscule amount of solar radiation received. The difference in solar energy between perihelion and aphelion could be as much as 20%. For a world where surface temperatures might only fluctuate by a few tens of degrees, this change in insolation could be the catalyst that kicks off a slow-motion seasonal cycle, potentially lasting for decades as the world approaches and then recedes from its orbital peak. The most likely manifestation of such a season would be the sublimation and recondensation of its most volatile surface ices. Imagine Quaoar approaching its perihelion. Over decades, the feeble sunlight would very gradually intensify. This might be enough to warm specific sun-facing terrain, particularly if it is dark and absorbent, above the critical temperature at which ices like nitrogen, carbon monoxide, or even methane transition from a solid directly into a gas. This wouldn't create a roaring atmosphere, but perhaps an impossibly thin, transient haze of molecules lifting off from the surface. This would be the Quaoar equivalent of spring and summer, a slow, silent thaw where the most volatile compounds abandon their solid state. This process wouldn't melt the landscape, it would ethereally vanish it molecule by molecule into a temporary gaseous shroud. These liberated gases wouldn't last long. Without a strong gravity to hold them, they would quickly begin to escape into space. But before they do, prevailing microwinds, driven by the slight temperature differences between the day and night sides, could carry them across the globe. They would eventually migrate toward the coldest places on the world, the permanently shadowed depths of polar craters or the hemisphere currently tilted away from the sun and experiencing its multi-decade-long winter. There, the gases would lose their minimal energy, condense, and fall back to the surface as a fine, bright frost, painting the winter landscapes with a fresh, reflective coat. This would create a slow but constant redistribution of material, a seasonal cycle measured not in months but in human lifetimes. The role of Quaoar's axial tilt in this process is another fascinating unknown. On Earth, our 23.5-degree tilt is the dominant factor behind our seasons. We do not know Quaoar's tilt, but if it is significant, it would add another layer of complexity to this already slow dance. A tilted Quaoar would have one hemisphere pointed toward the Sun for a large portion of its orbit, while the other languishes in darkness. This could create starkly different seasonal experiences between its northern and southern halves. One pole might be a permanent cold trap, continuously accumulating frost over millennia, while the other pole acts as a seasonal reservoir, gaining and losing its volatile ices with each long orbit. The interplay between its orbital eccentricity and its axial tilt could create seasons of wildly different character and intensity, a climatic symphony conducted over centuries. These theoretical seasonal changes could elegantly explain several of Quaoar's other enduring mysteries. The observed color variations over time could be a direct result of this volatile transport. As the summer sun vaporizes dark, irradiated tholins from one area, it could expose brighter underlying water ice, temporarily whitening that region. The subsequent winter would then deposit a new layer of darkening frost elsewhere. The unexplained brightness surges could be the combined reflective power of a vast new frost deposit settling over a polar region. Even the potential presence of a transient atmosphere would be a seasonal phenomenon in itself, peaking at perihelion and vanishing completely during the long, cold centuries near aphelion. Quaoar's seasons would be a silent, slow, and profoundly alien process, a cycle of change so gradual that from our perspective, it appears almost static, yet it may hold the key to understanding the dynamic and ever-changing nature of this most perplexing world. Now we arrive at a mystery that connects Quaoar to the most energetic events in the entire cosmos, a puzzle written not in light or heat, but in the relentless barrage of high-energy particles from deep space. As astronomers study the faint signals coming from this distant world, they've detected something deeply unusual in the way it appears to interact with cosmic rays. These aren't ordinary particles, they are atomic nuclei accelerated to nearly the speed of light by supernova explosions and active black holes, shooting across the galaxy and constantly peppering every object in their path. Normally, when these rays strike an airless body like an asteroid or a moon, they interact with the surface in predictable ways, creating a specific and measurable secondary signal. But the patterns observed around Quaoar are anything but predictable. They reveal an anomaly, a strange and inconsistent response that suggests this world is either made of something utterly unique, possesses a hidden magnetic personality, or is engaging in a form of physics we have yet to understand. One of the most immediate explanations points directly to Quaoar's enigmatic surface composition. Cosmic rays striking a surface produce a shower of secondary particles, and the nature of that shower acts like a diagnostic tool, revealing the atomic makeup of the material they hit. The strange patterns coming from Quaoar could be a signature of a surface rich in certain light elements or unexpected metals. For instance, if vast portions of the crust are covered in a thick layer of hydrogen-rich ices or complex organic molecules, the cosmic ray interactions would look drastically different than if they were hitting simple water ice or rock. The data might be telling us that Quaoar's surface is a bizarre chemical cocktail, perhaps laden with ammonia hydrates or methane clathrates in concentrations far higher than on any similar body. This wouldn't just be a curiosity, it would be a direct confirmation of the unusual chemistry suggested by its spectroscopy, providing a second, independent line of evidence that this world is a chemical outlier in the Kuiper Belt. But the answer might not lie in chemistry alone. Another captivating theory suggests we are seeing the effects of a magnetic field, a possibility that would be truly revolutionary for an object of Quaoar's size. Cosmic rays are charged particles, and their paths can be bent and deflected by magnetic forces. If Quaoar has even a faint global magnetic field, it could be creating a miniature magnetosphere, a protective bubble that actively shields parts of the surface from the full brunt of the cosmic ray bombardment. This would result in an uneven pattern of interaction, with some areas showing normal levels of radiation while others appear strangely quiet. The source of such a magnetic field is its own mystery. It could be the frozen-in remnant of an ancient field from when the solar system formed, preserved in Quaoar's interior. More excitingly, it could be generated by a present-day dynamo effect, which would require a conducting liquid layer deep inside, such as a salty subsurface ocean. In this scenario, the cosmic ray puzzle becomes indirect evidence for a hidden ocean, linking it to the thermal and geological mysteries we've already explored. We must also entertain a more profound and unsettling possibility that our fundamental models for how cosmic rays interact with icy surfaces are simply incomplete. All our knowledge is based on observations of closer objects like the moons of Jupiter and Saturn, or asteroids in the inner solar system. Quaoar exists in an environment unlike any we've studied up close. It is perpetually, unimaginably cold, and its surface ices might be in physical states we cannot replicate in laboratories. At temperatures hovering near absolute zero, the behavior of matter can become strange. Ices can become incredibly hard and acquire novel electrical properties. It's possible that the ultra-cold, ultra-dense ices on Quaoar are causing cosmic rays to interact in a fundamentally new way, perhaps producing secondary particles with different energies or in different proportions than our models predict. We might not be looking at a property unique to Quaoar, but rather getting our first glimpse of a universal physics of ultra-cold matter that only a place this distant and frigid can reveal. The implications of this cosmic ray puzzle extend far beyond Quaoar itself. If the anomaly is due to a magnetic field, it forces us to reconsider the interior structure and evolutionary history of all medium-sized dwarf planets. If it's due to surface composition, it reveals a previously unknown diversity in the building blocks of the outer solar system. And if it's due to new physics, it opens an entirely new field of study. These high-energy particles are messengers, and Quaoar is seemingly responding to them in a language we are only just beginning to decipher, a quiet but persistent signal that hints at the profound and hidden complexities lurking within this small, frozen world. And so we reach the final and perhaps most profound mystery surrounding this distant world, a question that stretches our imagination across billions of years into the future. After exploring its impossible rings, its missing atmosphere, and its puzzling geology, we now turn our gaze forward to ask, what is the ultimate fate of Quaoar? In the grand, slow-motion ballet of our solar system's evolution, where does this peculiar world's path ultimately lead? Will it continue its silent, steady orbit as a permanent fixture of the Kuiper Belt, or is it destined for a far more dramatic conclusion? The answers to these questions are anything but certain, and they reveal just how complex and unpredictable the long-term future of our cosmic neighborhood truly is. One potential future for Quaoar is one of remarkable stability. Its current orbit, while slightly eccentric and inclined, appears to be gravitationally secure for the immediate future. Computer models that project the motions of the planets and larger Kuiper Belt objects millions of years forward often show Quaoar continuing its lonely journey, largely unaffected by the gentle gravitational tugs of its neighbors. In this scenario, it would remain a frozen time capsule, a silent witness to the slow fading of the sun. As our star ages and expands into a red giant billions of years from now, the outer solar system will become marginally warmer, but Quaoar's great distance would likely spare it from being swallowed whole. It might instead experience a final, brief spring as its most volatile ices sublimate in the sun's dying warmth, only to refreeze one last time as the star collapses into a white dwarf, leaving Quaoar to orbit forever in a perpetual, deep freeze under the dim light of a stellar ember. However, this serene picture of permanence is far from guaranteed. The outer solar system is a vast and chaotic place, and gravitational stability over billions of years is an exceptionally fragile thing. The greatest threat to Quaoar's future comes from the same source that likely shaped its past, Neptune. The ice giant's gravity dominates this region, and its influence is not perfectly constant. While Quaoar is not currently in a resonant orbit with Neptune, the giant planet's gravitational reach is long, and their paths are not entirely independent. Over astronomical timescales, even the tiniest, imperceptible perturbations can accumulate. Through a process known as chaotic diffusion, a series of minuscule gravitational nudges from Neptune during close orbital approaches could very slowly pump energy into Quaoar's orbit. Over hundreds of millions of years, this could gradually increase its eccentricity, stretching its path into a more and more elongated ellipse. This wouldn't be a sudden event, but a creeping transformation that eventually pushes Quaoar into a realm of profound instability. This path of increasing eccentricity leads to two other, more dramatic potential fates. The first is ejection. If Quaoar's orbit becomes chaotic enough, a particularly close pass by Neptune could act as a gravitational slingshot, flinging it out of the solar system entirely at tremendous speed. It would become a free-floating interstellar object, a rogue planetoid destined to drift forever in the immense darkness between the stars. This is not a rare fate. Astronomers believe the early solar system ejected trillions of such objects, and the process continues at a much slower rate today. Quaoar could one day join this ghostly population, becoming a permanent wanderer in the galactic void. The alternative to ejection is a far more violent end, collision. A radically altered, high-eccentricity orbit could eventually cross the path of another large body. A catastrophic impact with another dwarf planet like Pluto, Haumea, or Eris is a possibility, though the vast emptiness of space makes such a direct hit statistically unlikely over the next few billion years. A more probable collision scenario would be with a much smaller object, but even this could be transformative. A high-speed impact with another sizable Kuiper Belt object could shatter Quaoar, breaking it apart into a new family of smaller fragments and perhaps creating a spectacular, temporary ring system of its own. It could be utterly destroyed or simply remade into a collection of new worlds. The reason astronomers' predictions vary so widely is that Quaoar's fate hinges on factors that are incredibly difficult to measure with precision from our vantage point. Tiny details make all the difference. The exact distribution of mass within Quaoar itself affects how it responds to gravitational tides. The precise orbits of other, yet undiscovered dwarf planets in the distant reaches could provide unexpected nudges millennia from now. We lack a complete map of the Kuiper Belt's mass, and we cannot account for every single gravitational interaction over such immense timeframes. Furthermore, models that include the subtle influences of galactic tides, the gentle pull of the Milky Way itself, and the occasional close pass of other stars paint an even more complex and unpredictable picture of the solar system's long-term future. Quaoar's journey is a single thread in this intricate tapestry, and its ultimate destination depends on the pull of forces we are only beginning to understand. Its fate remains one of the great, open-ended questions, a reminder that even in a clockwork solar system, the future always holds an element of mystery. From the rings that defy orbital physics to the puzzling absence of an atmosphere, from its leisurely spin to the complex relationship with its moon Weywot, Quaoar presents a tapestry of 25 profound mysteries that continue to baffle the brightest minds in planetary science. This distant world, a seemingly insignificant speck in the frozen darkness, has systematically challenged our most fundamental assumptions. It forces us to reconsider the rules governing ring formation, the very definition of a moon, the potential for geological activity in the deepest freeze, and the chaotic processes that built our solar system. Each unanswered question, from its contradictory density and uneven surface chemistry to its unpredictable brightness and potential hidden ocean, serves as a powerful reminder of how much we still have to learn about the vast, unexplored frontiers in our own cosmic backyard. Quaoar is more than just a Kuiper Belt object. It is a beacon of mystery, proving that the greatest puzzles are often found in the most unexpected places, urging us to look deeper and question everything we think we know. Now we want to hear from you. After this journey through the enigmas of Quaoar, which of its mysteries captures your imagination the most? Is it the impossible ring, the prospect of a hidden ocean, or something else entirely? Share your thoughts in the comments